I'm going to talk about animals that run, crawl, walk, and climb and fly, and synthetic nervous systems for their control. The biorobotics research process that we use is to learn biological principles from animals and apply those principles to improve robot mobility and autonomy, and use robots as models to test biological hypotheses. You can look at the functional approach versus the morphological approach, and in both cases, your goal is to replicate end behaviors. But the difference is with a morphological approach, we're really trying to use methods that are biologically plausible. And what you get out of that is a better chance of understanding the biology. It's a better model of the biology, therefore you expect to get a better understanding of the biology. This, the group at Case Western, it's been going on for more than 30 years. So I'm going to talk about that. I'm going to talk about the current work and future plans. I want to point out right at the beginning, biorobotics is not biorobotics without the bio. And at Case Western, I've been very fortunate to work with Roy Ritzman, Helen Schiller, and Mark Willis, who are in the biology department at Case. If you go way back to the beginning, 1988, their artificial insect project with Randy Beerhill, Sheila, and Leon Sterling, what they did was they developed a neural network, which was different from the neural networks of the time. It was based on the insect neurobiology as it existed at the time. And I got involved because they wanted someone to build a robot to test out the that neural network, and we did. And what was interesting was that it could produce the continuum of insect gaits that were well known at the time. And it was very successful, so we went on, and then here's a robot from 1995. You can see the compliance just now. Here's a stepping reflex. All this is autonomous. It's a distributed control system inspired by insect behaviors, implemented as a finite state machine. So you can see at this point, we stopped using neural networks. And I'll get back to that later. So here it is walking in a wave gait. This is a slow gait, one leg at a time. And then here in a moment, it's in the tripod gait, 3 legs at a time, forming 2 alternating tripods. And you could walk on the continuum of gaits in between those two. And here it is turning in place and crabbing. And in a moment, you'll see an elevator reflex. And these are all insect reflexes, again, well known, well documented. The turning and crabbing is actually unusual. It's more like a crab. Here's an elevator reflex, and the middle leg right in front of you. It's going to hit and back up and go over. It's a well-known reflex. And then here is a searching reflex. It's going to miss, and then it's going to pick up its foot, and it's going to search or purchase. And then just keep walking. Okay, so that was 1995. Cockroach legs are very different from those robots. They have 3 major segments, a coxa, femur, and tibia, but there's also a really large foot, this tarsus. We'll talk more about that later. There's this very small segment, this trochanter. So Roy Ritzman, back in the 90s, high-speed video, EMG recordings, and what he found was just exactly how all the joints on cockroach legs work, how they move relative to each other when it's walking and turning. And based on that, we developed this robot. This is a cockroach robot. This is a 97 to 99 era, and air cylinders for power. And here you see it's stable. It's got an active postural controller, and it's stabilizing it. It's a strong robot because the air cylinders, 5 joints in the front leg, 4 in the middle, and 3 in the rear, were enough to capture what Roy found in the insect movement. Gabe Nelson did the control system for this, who then went to work for Boston Dynamics, and he has become famous for the work he did in control of Big Dog and Atlas and various other robots there at Boston Dynamics. There's landmark papers backed by Low Brown and Chang and Gingrich and Fole showing that passive mechanics are really important for stability of animals. And this is a McKibben actuated robot. And this, right now, it has no active control. It's purely passive. And so we're showing it's you know, the passive mechanics are giving it stability. Robot. It's just 3 inches long. It's got 1 inch long custom fabricated McKibben actuators. It's a cricket. A bit larger than the cricket, but it's the form is very similar to a cricket. I love these two robots. I love this slide because it shows probably the clearest example of how bioinspiration has improved mobility. These two robots have the same mechanical design, yet the one on the right, Rex, has remarkably insect-like locomotion. And that's because Martin Buehler and company put this beautiful control system into it, so it actually just bounds along like an insect. So when someone asks, what has bioinspiration done for us, I'd like to show them this slide. So we saw that was back in 1999 when they first showed Rex, and we thought, okay, if we just mimic the function of a cockroach in the simplest way, what could we do? Well, cockroaches walk in a normal tripod gait, but they change the gait when they climb large obstacles. And they rear up before they climb obstacles. And they have a body joint for climbing when they're doing a transition like this, so it keeps them from high centering. So we want to put all that into a simplest robot, and we use the wheel leg idea. Here you see a 1954 patent with wheel legs, and then you see the flag of Isle of Man, which dates back to like the 13th century, apparently, the coat of arms. And I'm also told that during Roman times, they had wheel leg barrows, so they could push these things up and down the steps of Rome. So here wheel legs are actually quite old, quite ancient. So here's the a wheel. It's good at continuous, firm, smooth terrain. Here's the leg. It's good for discontinuous, uneven terrain. And here's the wheel leg. So it's sort of a combination of the two. You can get the leg cycle function with constant motor speed. So it kind of climbs like a leg, but rolls like a wheel. And here is our first Whegs robot, one of our first Whegs robots. It's walking along in a nominal tripod gait with just one propulsion motor through chains and sprockets. And then here you have the same robot, and it's changing its gait as it climbs because it's got these torsional springs in its hubs. So it's passively changing its gait while it climbs. And put in another motor for the body joint. So then you can use it to try to avoid high centering. And of course, there's another motor for steering. So there's one propulsion motor, one body joint, and one for steering. And then you can do all kinds of things with these things. Applications for the robot on the left is in an orange orchard. The robot on the right is in rubble. It's a search and rescue testing facility. And you can see they do really well. They do remarkably well in this really nasty terrain. All right, so now I'm going to move on to, here we go. This is the largest Whegs robot we built. It's about a meter long. And what's interesting about this is this body joint here. There's a motor that drives it so it can actively lift its front half of its body. But there's also bellbow washers here so that it can passively comply to the terrain. One of the problems we had was the body joints getting broken. So by putting this passive compliance in to solve that problem. And now you'll see there's the passive compliance. And here we have it climbing with a body joint locked climbs okay on this height with the body joint locked. If we make the obstacle just a little bit higher, has a tough time gaining in purchase here. And then it's going to actually fall backwards, and the pillow is going to come in to save it from a crash. Now we use the body joint and we make the obstacle even taller, and it can climb over it. This is all done with radio control. I do have some videos, which I'm not going to show you today, with autonomous climbing. And then here is a Whegs robot out in the Mars Yard in Montreal. And you see we changed the feet to this concave section so that it wouldn't, otherwise would bury itself in the sand. In loose sand with a regular foot, it would just pretty much bury itself. So with this concave foot, it can walk on the top of loose sand. All right. This is Mini-Whegs. Okay, so the idea is we want to make a robot, a Whegs robot, that go really fast. But we didn't want to lose climbing ability, so we had to give it a transmission. And here we have the primary component in this. We're using drill motors. It's a commercial off-the-shelf drill motors that have 3-speed transmission. So one motor and transmission goes here, another one goes here. We needed 2 of them because one of them wasn't powerful enough. The central gear here is shifts both transmissions at the same time. Here it is. If you can watch this inset, and you'll see right now it's in low gear. It's climbing over things. And then after it gets out of the sand pit, this gear is going to shift it to a higher gear for running faster. There we go. It just shifted, and it's just shifted again. And off it goes. Now it can go really fast. And how fast? Well, here is a student athlete being outrun by this little robot. And again, exactly how fast? Well, 25.5 miles an hour right there. It actually went as fast as 27 miles an hour, just a question of how charged the battery was. So how fast is it? Well, we put the word legged in quotes because it's really a wheel leg, so it's not exactly the same as a real leg. But if you call it a legged robot, then it beats all the other robots out there in terms of the legged robots in terms of speed. It beats in fact, it even beats a real, honest to goodness, cheetah when measured in bi-lengths per second. Because it's only got one motor propulsion, you can make these things, these Whegs robots small. This is Mini-Whegs, and here it's running around, going fast. And here it is out in the field, in the grass. And again, all radio controlled here. Here it is going down the stairs. Stairs are easy to go down. But how do you go upstairs? Well, Roy found a click beetle. And he did this high-speed video, and he showed that the click beetle jumps using its body joint. So instead of using legs to jump with the Mini-Whegs, we actually put more of a mousetrap kind of contraption on it. So here it is jumping up a stair. So other things you can do with Mini-Whegs, heck, you can make caterpillar Mini-Whegs. So this has got 3 segments. It's got tendons for turning and climbing. So this is fun with the concept of Mini-Whegs. These are just 3 similar segments tied together with tendons. All right, other things you can do is make climbing robots. So there's a gecko and there's a Mini-Whegs with, this is a structured adhesive, dry adhesive, they call it gecko tape. And that's the first time a robot climbed a vertical wall with a vertical glass wall with gecko tape. So here it is with Scotch tape to test it out before we actually got the structured adhesive. And here it is at like a 60-degree angle. That's Das Gorb's hand there, and you see his face. He came over from Germany to test it out. when we heard we had the robot operational. And again, here in a moment, you'll see it on 9 degrees, vertical glass. And this is 2005, so it's a very early version of the structured adhesive. And here, 2014 version of structured adhesive, and it works much better. It is a better robot in terms of it's a lighter weight. And you notice you don't need nearly as much structure of the material. The other one, we had to double up on the wheel legs. So the material has gotten much better, and so has the robot. Now, Stoth Gorb is at the University of Kiel. He's a biologist and also an inventor. Another thing you do with Mini-Whegs is make them fly. So he just walks off the building, takes to the air, flies around, changes colors. I joke because it's just a different robot here. Here it is flying around, and it's going to land, and here's landing, and then it's going to walk. And over here, you see the same robot. Well, actually, it's not the same robot. It's the same color, though. It's going to walk out the door, and to walk out the door, it needs to fold its wings because the door isn't held open wide. So anyway, the idea is this is the first small micro air vehicle that could also walk. And this isn't a Whegs robot. This is more of an honestly a six-legged robot. What's interesting about this, it can move around on that screen independent of the direction of gravity. It's using what we call distributed inward gripping, which is what insects use when they climb on walls and ceilings. The legs pull inward, so they oppose each other by pulling inward. And what's really important in this robot is the using a cockroach-like, insect-like tarsus. It's got that here, and these feet, these tarsi, are compliant, and therefore they don't get stuck in the screen. When we had rigid tarsi, oh boy, they just got stuck. Okay, another thing, of course, everybody wants to build is the micro flapping wing vehicles, and there's Delft. They actually have some beautiful ones. So we're working on making. The idea is to make a flying artificial moth. These wings here that you see flapping here, these are artificial wings. They have a similar venation, weight, and compliance of the actual moth wing. And when they're beat at the same frequency, which is roughly 25 hertz, is the moth, then they provide the same lift as the moth does. So we're successfully making artificial moth wings. And Ken Moses here, we just had a publication. You see how heavy this mechanism is. He now has built a beautiful little mechanism. Just one motor that drives a mechanism that flaps the wings like the moth wings flap to give us the same lift. Okay, so remember I said back in 1988 we were working on neural networks. And then we went to finite state machines for control. Well, in 2011, we went actually back to neural networks. And that's because there's been 20 more years of neuroscientific research with benefits of new technologies. In other words, high-speed video has gotten cheaper and easier to use. The recording technology has gotten easier. Microelectrodes have become accessible. So all the science that helps us build robots also helps the biologists, neuroscientists, record better data. So there's lots more data, and the question is, could we basically mimic can we actually use computational neuroscience to mimic animal nervous systems to create synthetic nervous systems? We coined the term synthetic nervous system to mean biologically plausible dynamic neural networks that as much as possible the same form and function of animal nervous systems. So the landmark paper for us, this was a landmark paper. This is out of Cologne. This is Ansgar Buschkes' lab. And this is a model of neuroscience that they and others have been doing for decades. And the point is, each insect joint has its own central pattern generator, and then sensory feedback coordinates the joints of the leg. And this is the details of it. So this was a landmark paper as far as we were concerned. And then another landmark paper was 2010, Kofer and al. Published on a software program called AnimateLab. What AnimateLab does for you is it models both the biomechanics, the dynamical system, so the biomechanics, the dynamics of the biomechanics, and also the neural system. And it's all drag and drop. So it models both. So you can actually you can model a neuromechanical system. You can design and model neuromechanical systems all in this one code. So that was a big deal. So it made it possible to do things that we wanted to do. Now getting back to the insect nervous system, of course, there's the brain up here, central complex right here, and then there's neck connectives, subesophageal ganglion, which is kind of like a brainstem in a mammal, and then there's the thoracic ganglia, the thoracic circuits here. So I'm going to call this the local nervous system, and up here is the brain, or the higher level system. And the question is, why not design synthetic nervous systems for robots? And do we have enough data? Can we do this? And so we started this project, and here is neuron 1, the green one, excited neuron 2, the orange one. These neurons are non-spiking conduction-based models. For the central pattern generators, we use persistent sodium channels. But the idea is, well, this is fairly well established. Oh, sorry, not fairly. It's a very well established model of a non-spiking neuron. So also, this is a fairly well established model, neuron model of a CPG. So here you see the extensor half center, flexor half center, then you see the inhibition from interneurons. And if you excite from a higher center, you excite these, and you get a nice oscillation going. And that's what you see here. There's no current input, so you get no oscillation. And then you get a little current, and it starts oscillating, and then it's sort of a linear increase in oscillation with current. So in other words, the robot, you can imagine standing here, you can imagine it walking here, you can imagine it running here, and going faster and faster. So we use the functional set network approach to design synthetic nervous systems. Neurobiologists perform intra and extracellular recordings to elucidate nervous system structure. We mimic structure and then tune the functional subnetworks directly by exploiting neural dynamics. We tune functional subnetworks. The idea is we don't build the whole thing and then tune it. We tune bits and pieces, one at a time. The resulting subnetworks can then be assembled into the large hierarchical networks and that actually function as intended, with no additional tuning. Bottom line is there's no naive optimization. We're not slapping together a giant network and then trying to optimize it to make it work. We're building it subnetwork by subnetwork. So all the parameter values can be selected directly based on the network architecture. And the interesting thing is you can add subnetworks and functions without retuning the rest of the system. We've showed that in at least one paper. Here is going back to roughly 2014. There's Nick Shashensky up here, who happens to be now at West Virginia University. He was a PhD student and postdoc at Case, and he also worked in Cologne. Now he's at West Virginia, just started there. But I love this particular set of slides because what you see here is one, this is a network for one leg. And there's 5 joints in the leg of a cockroach. And this is CPG, so you see 1, 2, 3, 4, 5 CPGs for 5 joints. And this fits in with 5 other legs just like it. All right, and then you also need interleg pathways. So there's the entire circuit for this cockroach synthetic nervous system. And here you see, here's a cockroach walking along, going forward, then it's gonna make a right turn. And here you see animal data. This is joint angle data, and this is the same joint angle data for the model. And what's interesting is you actually see similarities. You see these arrows here and these arrows here, and then you see these arrows here, these arrows here. You see similarities. You see these lines here and these lines here. There are similarities. It's actually, we're very pleased with these results. We also found that by modulating muscle control, you could actually change the radius of the turn. This is like 3 years later, in 2017. This is a new cockroach simulation with improved biomechanical model and improved interleg coordination. If you compare the two simulations, this one's just so much better. The other one looked kind of, just didn't look really good. It's kind of sticky. This one just flies along. So by adding the details, adding more biomechanical and neuromechanical, well, adding more neuromechanical details, we get much better results. This is Mantis Bot, and he's just standing there on his 4 legs and is being poked and he's showing his posture controller. What's really interesting to me, of course, in this 30-year history I'm talking about here, is this, all these green components here are made from, are all printed from polycarbonate. Back in the old days, they were either wood or machined aluminum. So the kids these days have it much easier that they can build things like this just by printing them. What you see here is the restepping reflex and the searching reflex in Mantis Bot, repeating things we did way back in 1995, but with a synthetic nervous system. And that's a big difference. Rather than just hacking it together with a finite state machine, this is the morphological approach, which, as I said at the beginning, tells us more about what's going on in the animal, and I think in the end will help us build better robots. Okay, so the most recent robot that we're building is Drosophibot. It's a fruit fly robot. It's 100 times larger than the fruit fly, but it's dynamically scaled to be similar. And more about that later. And there you see the robot, and there's the robots moving. So yeah, dynamically scaled, even though it's 100 times bigger, dynamically scaled to be similar to the fruit fly. So it's got 6 legs, 3 joints in each, 3 motorized joints in each, but there's also joints here, the tarsus. So we paid attention to the tarsus this time. The tarsus is really important in insects. There's a spring here that does a retraction, so instead of putting a motor there, we put a spring. More about the tarsus later. Here, more about the tarsus here. Insects have these long compliant foot segments, and they increase the overall ground contact. They're really important for gripping, and they're also important for absorbing impact. Without the feet segments, the robot sits much closer to the ground, and the kinematics are all wrong. So in the Drosophibot, we put the tarsus on there. And here's some close-ups, and you see there's multiple segments here, and there's ball and socket joints in between the segments, so that you get the compliance that you see in the insect. And again, you see the cable and the spring for their restoring force. So we're using a dynamic morphological controller for Drosophibot. It's similar but improved to what you saw for the cockroach. Again, when there's more learned about the insect's thoracic ganglia, we incorporate it as soon as possible into the synthetic nervous system. And we're using AniMatLab to do all this modeling, but we're also using AniMatLab. We simulate the network in AniMatLab and control the robot in real time. Mass scales with length cubed, muscle membrane stiffness scale with length squared. What that means is for very small creatures like insects, that the elastic forces dominate over the inertial forces. And what that means is if you have this is a joint on an insect, if you pull it down and let it go, it bounces back. So we wanted the robot to do that as well. So we put springs in parallel in the joints. So there's a spring at each of these motorized joints. Now, dynamic scaling, we use the Struhel number. And this, what we've done is we've made the Drosophibot Struhel number to be similar to the animal's Struhel number. And what that tells, and we of course want both robots then to work in the elastic regime, like we know the animal works in the elastic regime as I just described. We want the robot to work in the elastic regime, and by matching the Struhel number, that's what you get. And you see the Struhel number squared is greater than 1, elastic regime, and you see the idea is that joint stiffness is large compared to the inertia of the limb. And also, if you want them to move in the same time scale, then the Struhel number tells you what to do there as well. So the period of cycling the legs of the robot is smaller than that for the animal because the robot is so much larger. Insects have these campaniform sicilla, which are basically strain gauges, and they're extremely important in the animal and also in the robot. So Sasha Zill at Marshall University, we worked with him in the past and we're working with him again. He knows a lot about where the strain gauges are on these animals, and there's several groups here, which is where the trochanter would be, but we don't really have a trochanter. We put it on the femur, and then also here on the tibia. Now, insects, when the insect is the cuticle is bent, the sensor encodes the campaniform sensoric encode the amplitude of bending. They also encode the rate of bending. So that's something we want to capture. The other thing that's interesting is once you put strain gauges onto a robot, what you find, of course, is you got a large load when it's standing, and then it's hard to pick up the small changes of load and the rate of loading. So we developed this filter. That processes strain signals such that it adapts to the constant loads. Okay, so results. This is for the joint controller. What you have here is a paper by Aka and Matheson in 2013. And what you see here is a femur tibia angle, plotted versus time. And with one motor neuron spike, that's this asterisk, one motor neuron spike, it causes the joint to rotate, but then it's only one spike, so then the passive forces take over and it just springs back. And we do the same thing, one motor neuron spike, and we have the same thing happening, and then it bounces back. And if you do 1, 2, 3, 4, 5 motor neuron spikes, and here's the animal, and it works as, jagged on the way down, then it goes back up because elastic forces. We do the same thing, 5 in a row, 5 motor neuron spikes in a row, and we see the same jagged and back up. And then here we have, in the animal, in the experiment, they did 5 quick, much closer together, so fast spiking, and you see this is what you'd expect. We did the same thing here with 5 rapid, and you see the same kind of thing happening in the robot. Proprioception, well, here's the angle, here's a femur tibia angle of flexion and extension, and over here we see extension and flexion. And then you look at angle encoding and velocity encoding neurons. This is angle encoding neurons across here, velocity encoding neurons across here. This is for the fruit fly, and this is for the robot. And you see remarkable similarity. You look at the red here, look at that shape. Look at the red over here, that shape. And you look at the blue here, that shape, and the blue here, that shape, very similar. And you look at the blue here and the blue here. We see we get matching. And down here, for velocity encoding, over here they did not encode, they did not record from extension. We can see reflection. You see velocity encoding neuron here, and here for the robot, and here for the animal, and here for the robot. You see we're capturing details of proprioception. Strain filtering, well, we apply a force in green, and you see this sensory discharge in yellow, and the same thing over here for the robot. Applying a force, and you see the sensory discharges. The other thing is when you look at this is rate of change of force, loading rate, basically the same thing. So these two plots, this is for the animal and this is for the robot. These two plots are comparable. And here you see it's basically linear, and here it's basically linear. It's encoding for rate of change of force. Okay, moving on. Now, getting back to the idea of the synthetic nervous system. Here's the brain of an insect, and here's the central complex, subesophageal ganglion, and thoracic ganglia. Things that we now know that people like Roy Ritzman and others have figured out is that what's happening is the brain sending down descending commands that modulate the local controller. The brain is not it's not a centralized controller that's telling the local circuits everything to do. They're just sending down commands that then modulate, and then the local controller then changes the system from like forward walking to turning or climbing or whatever. So here's Roy Ritzman again, and what's the role of the brain? Well, here's an intact animal. This one has the brain severed from the subesophageal ganglion, so the neck connectors are cut. Notice the antennae are dragging back. What really goes wrong is it does not do a good job of postural control with a brain severed. And the other thing it does is it just walks forever until it dies. Basically a zombie. So yeah, it doesn't handle the postural control without the brain. And here we have, and the cockroach is off to the right. Roy's lab, they record from the brain using microelectrodes. They're recording from the central complex. And what you're hearing are actually units in the brain firing. Listen. Here the spike comes. So that's a unit that's clearly involved and encoded for climbing. I've done a lot of really exciting work. For example, here's they found a unit here that's important for left turning, which is encoded for left turning. This one's encoded for right turning at a higher speed. This one's encoded for both left and right turning. So this is really exciting work, actually recording from the central complex using microelectrodes. Starting to get a picture of what's going on in the brain. Okay, here's a praying mantis, and those are cockroach nymphs, and you know what's going to happen. The praying mantis actually focuses on one and just hunts it. Just keeps it's just tracking that one, and it's eventually going to munch it. So that's tracking prey. Well, remember that praying mantis robot. Here, instead of tracking a cockroach, it's got these light-sensitive diodes here, and here we got a light, so it's watching. It's got a neck, it's got its head, and it's got a neck back here, and it's tracking the prey, which is a light, and it's got the one leg operational here, and that leg is doing the right things that would cause the robot to move toward the prey. So the idea here is the descending commands from the head sensors are modulating the synthetic nervous system we have for this thoracic circuit. In fact, it's all a synthetic nervous system, so with the descending commands modulating the local system. Now, I'm moving on to rats, and 5 years ago, we started working with Martin Fisher. Maybe it was longer than that, maybe 10 years ago. We started working with Martin Fisher at the University of Vienna. And he has high-speed video X-ray equipment, and that's what you see here. And if you watch, there the one foot just went down in a hole. The rat can't see the hole. Here it comes, right there. The rat can't see the hole, so it's a surprise to the rat. Here it goes again. What's interesting is they also record this from here. They're recording from some of the muscles. And what's interesting, you see this pattern going along, and you can tell there's an expected point of touchdown for the foot, and the foot doesn't touch down because it's got in this hole. And what's amazing is in like 5 milliseconds, it recovers. The fact is this expectation of touchdown indicates that there are in fact CPGs, but the fact that it reacts so fast to a disturbance such as this indicates that the sensory pathways really take over instead of the CPGs just marching along. So it can reset the CPG. Here is Alex Hunt, who did a model of well, a synthetic nervous system for the rat hind legs. And here is for one leg. Here's a synthetic nervous system. This is simplified, it didn't show everything, but this is for one rat hind leg. And the connectivity came from the literature, purple connections from this Pearson 2008, blue connections for Prohaska 97, brown connections from McBee 2005. The black are from our own observations. So there's just these two, actually these four that we put in, but the rest of them came from the literature. And then for the interleg coordination from cats and mice, here's a left leg, here's a right leg, hind legs, and then here's the interleg coordination. And again, all the green connections came from Akai, publications from Akai, and the gold connections here, all these gold connections came from a paper of Telpolar. And you see a black one there and a black one there, and those are our contribution. And here we see rat walking along, and it's going to get perturbed here in a moment. Here's coordinated walking right now, and it's going to get perturbed, boom, and now you see it's been perturbed, but then it gets back into coordinated walking. That's with the synthetic nervous system. And then we found two sets of data. Two sets of data for rat walking, which was different. It's really trotting, is what they say. Anyway, they're different. The gait is different. And what Alex found is that by changing just one synaptic conductance, he could get either this gait or this gait, just by changing one conductance in a synthetic nervous system. And then here's more rat work, and there's literature on resetting deletions. And the idea is this is the hip, knee, and ankle of the rat model. And then there's a perturbation here. See the perturbation happens right there. And then after a while, it comes right back to where it was over here. So the point is that it resists, well, it resets after this perturbation. So the gait is maintained. It resets and the gait is maintained. And to do this, we had to actually improve our synthetic nervous system model to something that Ryback has published quite a lot on. It's a two-layer structure with a rhythm generation network and a pattern formation network. And here is our Greyhound robot. Just rear legs are being controlled here with the synthetic nervous system. The speed of the treadmill is changed and it adapts to the speed, no problem. When Martin Fisher saw this, he thought this was fantastic. There we go. There's a sudden change in the treadmill speed, and no problem, it adapts. So Martin Fisher, who's an animal expert, in particular dog expert and rat expert, he thought this was great. Okay, so now a little bit about worms, soft robots. This robot has just one motor. It's kind of like the Whegs of worm robots. It's got one motor, and it's got tendons that come back to a cam. The motor rotates the cam, and there's 12 of these tendons. And as it pulls on the tendons, it creates these has these beautiful peristaltic waves. They run down the body, and as they run down the body, moves the robot forward. But that was just with one motor. This is with one motor per segment. And the one motor per segment means that you can do lots of other things. It's not just a stereotypical kind of wave. You can actually make it change based on the terrain. If it's going through a tube, for example, you can get smaller and where you need to go smaller. So you put sensors on it and have it locomote based on the terrain. What you see here is a lot of vertices, and there's tubes connecting the vertices, and the vertices are printed. They're hard plastic. Well, the idea was to get away from the hard plastic, so we found that, well, this is fabric worm. The idea is you could use cloth, which is stretchable in one direction. So it's actually part of the structure of the robot now. It provides some springiness that's needed, and then you can sew the tubes right into the fabric. So the fabric, I said, again, it provides much of the structure. In fact, we have another one that's what we call mini fabric worm that has almost no hard components in it at all. And this is something completely different. It's the idea that you can harvest sea slug muscle and build a robot that can actually live for a while and move around. So it's sort of a Frankensteinian approach. And this is Vicki Webster Wood, who's now at Carnegie Mellon. This was her dissertation. So this is indicating that the robot actually moved. What's really interesting, well, one of the things that's interesting about this, and I'm going to attempt to show that now. I'm going to attempt. Okay, so this is our only robot. Its own music video. This is an Irish band called the Jangleros. We just got an email from these guys recently to let us know that they did this music video based on our publication. Okay, so you get the idea. I'm going to jump back to the other thing. So anyway, that's our only robot that has its own music video. All right, so you see, if you want to look that up, it's by the Jangleros right there. Okay, so more near-term applications. Well, the control systems that we've been developing, especially the finite state machines, the control systems we develop using finite state machines. The basic architecture we're using works really well for autonomous vehicles. Of course, it works really well for animals, so I suspect we're not surprised it worked well for autonomous vehicles of all sorts. This was our urban challenge contestant back in 2007 called Dexter. And it did actually very well. It ran around tracks and didn't run into any vehicles, didn't run into any walls. It worked very well. There we go. This is an autonomous snowplow. It's a GPS denied area. So therefore, we use ultra-wideband beacons, SICK LiDAR there. But I'm just showing this to point out that the concepts we learn from animal architectures and their control can be applied elsewhere. And also, we're developing an exoskeleton for walking assistance for people with spinal cord injuries. And we're using the muscles to provide most of the force, but then we put motors on to assist the muscles as necessary. Here is an able-bodied person. This is an able-bodied person, and this is one of the many tests we did with this device with many able-bodied people to verify that it was safe to use. Of course, there's a control system with it that it has gate event detectors, and you have to make sure that it's safe and it actually performs as necessary, as it should. And the newer version actually has ankles as well. And our goal is for it to be self-stabilizing. Now here's future work. We are just starting a project that's funded by NSF in this country and funded by, in the Germany and the UK, funded by governments there. So it's a large project, and the idea is to address the question, how do biological nervous systems control and execute interactions with the environment? And not just looking at one animal, but looking at 3 different animals, very different animals. They're from 3 different phyla. There's a rat, the fruit fly, and the sea slug. And they're from different phyla. They operate in different, this is a length scale versus a time scale. And the idea is over here, animals and robots would be inertially dominated. And over here it's quasi-static, and down here it's viscous, the dominance. So you see the Drosophibot walking is down in here, where the plesia swallowing, the grasping and eating is over here, and the rat walking is up here. And dogs just a little bit above that. So you can see what we're doing, looking at the animals, but also using the robots as models. And we'll be doing computational neuroscience to go along with that. And it's a big program. There's Case Western, Carnegie Mellon, Northwestern, West Virginia, Portland State, and Emory in this country, and then Cologne, and Würzburg in Germany, and Lincoln in the UK. So we're looking forward to 5 years of that. Communication, coordination, and control, C3NS. So this is just a little summary, things that, some of the things you saw and hopefully enjoyed seeing. And that's about all. So I want to point out and say that what you saw, just about every slide was like another publication, and a lot of work. And then you heard about Roy Ritzman. Unfortunately, Roy Ritzman just retired this year, so that's very unfortunate as far as I'm concerned. Mark Willis is still going strong. He's working on the moth. Ansgar Bushis, we're working with him on the NeuroNext project. Stas Gorov, we work with him once in a while. He's at Kiel. Ravi Vadnathan, he's a former student and he's in the UK. Hillel Cheel, he's still going strong in biology at Case. Sasha Zill, you heard about him, he's at Marshall. And Martin Fisher, still at Jena, and we're really looking forward to working with him, continuing to work with him. This is an old photo of, I don't know, from like 2009, I think. And then here's a group lab photo from 2015 when I still had a beard. But the recent photos look pretty much the same. Faces slowly change as people graduate. And I shave my beard or whatever, but it's basically the same. A lot of people doing what I think is a lot of really good work. So that's all I have to say. I hope to talk with you live tomorrow morning.